We have one last new thing to go over with this unit, and that's called empirical formulas. This is a formula that you can calculate based on lab data. So that's what we're going to be doing in our next lab, which is going to be a long one. It'll take parts of 3 days. And we'll start with a definition. The empirical formula, empirical is a word that means from data or from experiment, by the way. The empirical formula is the lowest whole number ratio of atoms of elements in a compound. This is the formula that you can calculate or come up with based on lab data. That doesn't mean that it's always the exact right formula for the compound. Because if you took a compound like glucose, maybe something you learned about in biology, C6H12O6, that's glucose. It's a kind of sugar. This is the energy that your body runs on for the most part. 6 and 12 can reduce. So the lowest whole number ratio for that compound is 1 carbon for 2 hydrogens for 1 oxygen, 1 to 2 to 1, if you reduce the 6 and the 12s. The empirical formula would be the second version that you see there. So the formula that you would come up with based on lab data would be CH2O. We know that's not the exact right formula for glucose, but that's the lowest ratio of those atoms in the compound. We calculate empirical formulas based on percent compositions. So that's why we started with percent composition before we moved on to empirical formulas. And it could be of a new compound or of a compound you haven't seen before. And then based off that percent composition, we can figure out what the formula of that compound might be. So as we go through these steps for solving for the empirical formula, remember that we're starting with a percent composition. That's our starting point. That's the information that we already have, or we are presuming that we already have. So if you're given a percent composition, it's given as a percent. Because percents are always out of 100, we can make our math a lot easier by assuming that we have 100 grams of the compound to start with. What that allows us to do is then take that percent number and simply swap the percent sign for a grams. If we assume that we had 100 grams of the compound to begin with, then whatever percent number we have, we can just change that percent sign to grams. Step 2 is to take those gram numbers for each element in the compound and convert them to moles. This is something we already know how to do. You just need to look up the molar mass from the periodic table. Step 3, take each of those mole numbers and divide them by the lowest of the mole numbers. This is a step that's going to make a little more sense when you see it, when we do some examples. Look for your lowest mole number, divide everything else by that lowest number. That will give you a series of decimals, which we will round to whole numbers or manipulate so that they are whole numbers. And once you've got whole numbers, then you can write the chemical formula. So next we have 3 examples to do. I think the examples may be out of order on your page. I think I rearranged the PowerPoint slides so they're in a different order. So find the one that has fluorine and lead. Based on lab data, we would have been able to calculate that this compound is 26.8% fluorine and 73.2% lead. The first step to finding the formula for this compound is to take those percent numbers and change them to grams. So if we start with the fluorine, all we do is take the percent sign away and put a grams in its place. Step 2, convert grams to moles. So we need to cancel the grams. So where do they go? On the bottom. And what number should we put there? The mass of fluorine. So we look it up. The mass of fluorine is 19.00. And we know that that's the number of grams in 1 mole of fluorine. So we put 1 mole on the top. Those 2 numbers are going to be divided. You should end up with 1.41 moles. Now we need to do the same thing for the lead. Step 1, change the percent to grams. So 73.2 grams of lead. And step 2, change those grams to moles. Look up the molar mass for lead, 207.2. That's the number of grams in 1 mole. These are going to end up being divided, and you should get 0.353. Now we're ready for step 3. Step 3 says divide all of your mole numbers by the lowest of the numbers. So which one is lower? 0.353. So that means we're dividing both of these things by 0.353. What's that going to make on the bottom one, on lead? 1. So we know one of them is going to come out to be a 1 every time. If you do the top one, you end up with approximately 3.99. Step 4, change to whole numbers. Whole numbers are probably going to be 4 and 1. This one's pretty easy. All you have to do is round. 3.99, pretty obvious. That's going to round up to 4. And of course, the 1 is almost exact. So we have 4 and 1. These are the numbers that you use to write your formula then. Step 5, write your formula. Now you do have to decide which of those 2 atoms is going to be listed first, or which of those 2 elements will be listed first. The metal goes first. The positive charge goes first. So which comes first? Which one? Lead. Because lead is a metal and because lead has a positive charge. So there's 1 lead. And then how many fluorines do we need? 4. So your formula, which is your final answer, is PbF4. Now, before we move on to the next one, let me ask you a quick question. Are there any sig figs in your final answer? No. So, does it really matter how many you keep here and here?
Yes.
No, not so much, because there's no sig figs in your answer. So, for these kinds of problems only, I'm not checking your sig figs because it doesn't affect your answer. You'll probably end up doing them anyway just because you're so used to doing them at this point, but you don't have to worry about whether or not you've got them right. Next one, find the problem that has potassium, manganese, and oxygen. We're going to do this one the same way. The only difference is that it has 3 parts instead of 2. Step 1, change the percent to grams. We'll do potassium first. Step 2, change the grams to moles. Look up the mass for potassium, 39.10. And divide those 2 numbers. We need to do the same thing for manganese. Change the percent to grams. Change the grams to moles. Look up the mass for manganese, 54.94. Divide those 2 numbers. And repeat one more time for oxygen. Change the percent to grams. Change the grams to moles. Look up the mass for oxygen, which is 16.00. And divide those 2 numbers. Of the 3 that we have now, which one is the lowest? Manganese, 0.508. So that means everything should be divided by 0.508. Of course, manganese is going to come out to be 1. Potassium comes out as 2.01, and oxygen is 3.996. Now we need to change these to whole numbers. 2.01 rounds off to 2. 1, of course, stays just 1. 3.996 rounds up to 4. And now we need to write our formula. And again, we're going to have to choose what comes first. We know that it has to be a metal. We know that it has to be a positive charge. Question?
No. What's the answer?
Oh, okay. Which one?
Potassium.
It would be potassium, but how do we decide between potassium and manganese? Both of them are metals. Both of them are positive.
Transitions metals.
It doesn't have to do with the fact that it's a transition metal. If we have 3 elements in a compound, that means 2 of those elements are probably part of a polyatomic ion. Where do you have a list of polyatomic ions? On the back of your notes packet. So once you get down to making the choice, is it potassium or is it manganese? One of those things is going to make a polyatomic with oxygen. So you've got to go to your list and look at the list. Is there something on the list that's got a K and an O? Or is there something on the list that's got M, N, and O? M, N, and O. MnO4 should be permanganate on your list. So that's how we know, because permanganate has a negative charge as a polyatomic, so that's going to come second. That means the potassium has to be listed first. So K2MnO4. We've got one more example to do. There's going to be a little twist at the end of this one, but the beginning starts the same. This time we have manganese and oxygen. Here's where you may want to ignore your sig figs, because how many sig figs are in each of these numbers right now? 1, and that's not going to help very much when we're doing our calculation. So you may not want to do sig figs on this problem. Step 1, change percent to grams. Step 2, change grams to moles. Look up the mass for manganese, 54.94. Divide those two numbers, and you get 1.27. Repeat for oxygen. Change the percent to grams. Change the grams to moles. Look up the mass for oxygen. It's 16.00. Divide those two numbers. Which is the lower of the two? 1.27, so we need to divide both of them by 1.27. And of course the top one, the manganese, is going to come out to be 1. But look what happens with the bottom one. We get 1.48. It's almost exactly halfway between rounding down and rounding up. It's almost 0.5. If you get one that comes out to be 0.5, it's not as simple as just rounding up or rounding down. The reason is because you're rounding too far. It's too much. That's not going to give you the right ratio of atoms in your compound. So we need to fix this. What is 0.5 as a fraction? 1 over 2. Okay, 1 over 2. If I wanted to take 1/2, 1 over 2, and multiply it by something so that the 2 goes away, in other words, so that the 2 cancels here, what would I multiply by? 2 over 1. Because if you do this, then you end up with 2 over 2, which turns out to be 1. It's kind of a roundabout way of saying we're going to multiply both of these by 2. Because if we multiply by 2 on the bottom, that half goes away. And we end up with a whole number instead. So multiply both of them by 2. It's kind of like algebra. Whatever you do to one, you got to do to the other. Multiply both of them by 2, and the correct ratio for this compound would be Mn2O3. If you go on to take college chemistry, you will learn that you need to multiply by 3 for a third, and 4 and 5, and so on. I'm not going to give you anything that complicated. The only one you might have to multiply for would be if you get a half. So watch out for the halves.